Okay, so are you really getting cold? I just said that on video. Okay, so today we are going to be looking at some net ionic equations. And in order to be successful in net ionic equations, which were probably your least favorite thing last year, I can once I start doing it, you'll be like, oh, I hated these. But you'll like them better because you'll be better at them, and it's not as hard now because you really understand more than you think you do. But one of the most important things this year that you need to really, really memorize, and you're going to be relying heavy on this information, are these solubility rules. I'm going to combine a few. I don't really like necessarily how these are put together, but it was the only electronic one I had that I liked. We're going to start with this first rule, and I want to kind of combine Rule 1 and Rule 4 together. Rule 1 and Rule 4 are the Big Daddy rule. Together it's the Big Daddy rule, not R. Focus more on nitrate, that is acetate, and alkali metal salts. Those are going to be your most common. Yeah, it's nice to know that ammonium salts, chlorate, perchlorate are always soluble, but they're not as crucial. It's the nitrate and that alkali metal. Man, you see that constantly. Okay, so those salts are always soluble. So what this table is, I should back up a little bit, is looking at different ionic substances and determining if they are soluble in water or not. That's what we mean by solubility rules. If everyone looks up here above the board, you see the little guy in the pink suit, the pimp, the cartoon here? That's Big Daddy. He's got the cane, he's got the hat. He takes precedence over any other of the solubility rules. Okay? All these characters up here you will know by the end of the year. They all have a little meaning. We'll get to them. But today you get to meet him, Big Daddy. All right. So moving on to the next rule. This is a good one to know. You can kind of don't worry about number 3 much at all. I want you to focus on these 3. What do chlorine, bromine, and iodine have in common? They're all what? They're halogens. Because they're halogens that have a charge, we call them halides. So halides are all soluble except for silver, mercury, and lead. I have a little saying for those. Hal, which stands for halides, hugs Aggies pretty badly. My sayings are horrible, but they work. So if you come up with something better, that's fine. All halogens or halides are soluble except for mercury, silver, and anytime you see pretty badly together, that's how I call lead. Mercury, silver, and lead. Here's Hal, right there. He's got an A&M helmet under his arm, and he hugs Aggies. Since I'm a Longhorn, I used to have Hal hates Aggies, but someone mentioned that the G in hugs makes the mercury make more sense. Okay? Like, bless your heart. Yeah, I got it. Bless your heart kind of hug. Okay, so those are halogens or halides. Another rule that's really good to know is your sulfate rule. All sulfates are soluble except for all of those. This is pretty much the worst saying I've ever done, made up in my career. But I was desperate, so here it is. Sol is a name for sulfates. Sol, can, bag, hags. Pretty badly. Oh, it gets worse. In Sri Lanka and Argentina. So from this horrible saying, we know that all sulfates are soluble except for calcium, barium, mercury, lead, strontium, and silver. There's Saul next to Hal. He's bagging an old hag, putting her in a bag. And he's got a name tag that says Saul, and he's pretty evil. So anyway, those are the solubility rules. That last one, you know, look at it, kind of get familiar with things, that these things aren't usually soluble unless Big Daddy comes into play and they're attached to any group 1 metals. But just kind of look at it, get familiar. Do I think you should sit there and memorize every single one of those? No. You're going to become familiar with the ones that are soluble, and in doing that, you can kind of rule out the ones that aren't. Okay? So let's apply this to something so fun, net ionic equations. Oh, not yet. First, we're going to do this. We're going to practice our solubility rules. So I'm going to go through, you're going to go through and tell me this is soluble or not soluble in water, these salts, and tell me why. So A, silver nitrate. Yes or no? Yes. Why? Big Daddy, nitrates are soluble, right? All nitrates are soluble. Sodium chloride? Yes. Why? Big Daddy, group 1 metal salts are soluble. Lead 2 bromide. I'm good. I don't want to cough because then you all think everything's on the test. That's bad. Lead 2 bromide is not soluble because we're dealing with halogens, right? So all halides are soluble except for silver, mercury, and lead, and that is lead. So not soluble. Ammonium hydroxide. Yeah, why? Big Daddy, NH4 is soluble. Barium sulfate. No, all sulfates are soluble except for can bag hags. Barium. So calcium hydroxide, remember from yesterday, that's the one that can go either way. So we can say dilute solutions, yes, saturated, no. But again, I don't want you to freak out about this. You can go either way with that on the AP and be fine. And then lithium carbonate, yes, Big Daddy. Big Daddy, group 1. Group 1 metals. Okay? So now let's do some practical application with this whole net ionic thing. So do y'all remember what this is about? We had these equations, and you wrote out the molecular formulas first with the states of matter next to them. And then you took the second step and split the things up into ions that could be ions. Remember? And then what did you do in the third step? You crossed out, what were those things called that you crossed out? Spectator ions. Very good. All right. So this is not as bad as it used to be, though, I promise. You'll be surprised how much better you are at this than you were then. These are going to be primarily single and double replacement reactions right now. Unit 3 is our big reaction unit, and we're going to tear reactions apart, and you're going to really dig deep. But for now, I just want you to get used to this. The good news is, after you go through this mini hell with these long versions of this, Unit 3 is me teaching you the shortcut to how to do this. But you're not ready for the shortcut yet. We got to go through this one more time, and then you'll appreciate the shortcut even more when we get there. But double replacement, who remembers? It's just the two components of each of the molecules literally swap places. Single replacement, and you have a single element that'll try to boot out another element. What did you always have to refer to when you were doing that, though? This activity series right here. Okay, you have to look at the activity series for single replacement reactions only to determine whether or not the reaction is going to happen. We're only doing this unit because guess what? On the AP, all the reactions happen, so we don't ever have to look at an activity series. I want you to know its existence. I want you to understand about reactivity issues. But after this, we're going to throw the activity series out the window. So let's go ahead and start with the first one. We're going to write the reactants out, put the states of matter next to them, and then predict the product. So potassium chloride, what's the formula? KCl. And is that soluble in water? Yes. Since it's a salt that's soluble in water, in this particular reaction, it'll be, who remembers what we wrote? Aqueous. What are our options? Solid, liquid, gas, aqueous. If it comes straight off the periodic table, you use whatever form of matter it is that you're taking off. Hydrogen's a gas, so you put a G, that kind of thing. Molecular substances like CO2, use the state of matter that makes common sense. What's CO2? A gas. H2O, liquid, okay, because those are pure substances, so you use solid, liquid, or gas. You use the HQ only in the solution form. Lead 2 nitrate, PbNO3, is that soluble? Yes, so we write aqueous. Now we're going to predict our products. This is a what kind of reaction? Double replacement, so we get, good, KNO3. And that is aqueous because of the Big Daddy rule. Nitrates are always soluble. And what is our last product? PB. Why am I Cl2? Can't lead be 4? Exactly. It started with 2. We use 2 at the end because double replacement reactions can never, or aren't redox. Oxidation states do not change in double replacement reactions, so we leave it as 2. And then, is that soluble? Halogens, nope. Hal hugs Aggies pretty badly. Pretty badly, that's not soluble, so we write S for solid. All your ionic substances are solid if they're not aqueous. There's no liquid salt running around unless you're at a really, really hot temperature. Okay, so now we make this happen and we take what we can split up into ions and split it up. I'm going to do this on 2 lines. I'm going to do the first reactants on one line, products on the other, because I don't have a ton of room. But before we do this, I've got to do something else. I'm going to have an issue if I don't. Got to balance this equation. So we have 2 nitrates, 2 potassiums, 2 potassiums. Now my chloride's balanced. All right, here we go. Splitting this up. I have 2 K pluses. So when this ionizes, it's like I get 2 potassium ions and 2 chloride ions. And they're both aqueous. Plus, this totally ionizes because it's aqueous, so I get lead 2 plus 2 nitrates. Those of you who don't have a super strong background, I need you all to really pay attention to this. A lot of students will write NO3 with a subscript here. No, 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 no. This whole thing splits up. All the ions split up separately. So you have 1 lead and 2 nitrate ions floating around. Okay? So you've got to bring the subscript from the polyatomic down here up as a coefficient. All right, that's the first line. Now we're going to go to the products. I have 2 K pluses split up because that's aqueous. And then again, I have 2 nitrates split it up because that's aqueous. Lead 2 chloride, what do? Leave it because it's solid. It does not dissociate in solution. Yay! Now I can get my net ionic by canceling out things that are the same on both sides. By the same, I mean same in number, same in charge, same in state of matter. If any of that is different, you either made a mistake in balancing, or you might have written the wrong, or it just doesn't cancel. Okay? If an oxidation state changes, it doesn't cancel. It's not the same anymore. So what is the same? Potassiums can go, and nitrates can go. So now I rewrite my final net ionic, and I get 2 Cl minuses aqueous plus Pb plus 2 aqueous gives us PbCl2 solid. Okay? Does that seem a little bit easier? Okay, now we're going to go through this next one. We'll do all 3 of them on this page. Starting with silver nitrate, what do I write? AgNO3, is that aqueous or not? Yes, it is, absolutely. Magnesium bromide, MgBr2, aqueous or not? Yes, I know it's a halide, but it's not silver, mercury, or lead, so it is soluble. And then we get a double replacement reaction. So what's one of my products? Silver bromide, AgBr, soluble or insoluble, aqueous or not? It's not. Hal hates Aggies. Solid. Plus MgNO3, 2, and that's nitrate, so it's aqueous. One of those shortcuts we'll be doing is anytime there's a nitrate, you're not even going to write it down anymore. You're going to love the shortcuts next unit. Despite how organic chemistry says they hated the unit, don't listen to them. They're crazy. Those crazy seniors. All right, do we need to balance this? I think we do. I see 2 BRs, so I'm going to make 2 BRs. That makes me need 2 silvers, and that takes care of my nitrates. All right, so 2 Ag pluses, aqueous, plus carry that 2 over to the nitrate. I meant to change colors. Darn it. Plus, can I split up magnesium bromide? Yep, Mg plus 2 aqueous plus 2 Br minuses. Don't write Br2. Don't do it. Br2 is a liquid, and that's not what's happening here. Br is actually part of this lattice, and it's going to break into ions, okay? So we have 2 Br minus ions. So that is my reactants. Those are my reactants. 2 Ag pluses. Oh, can I split that up? Nope. You'll have to stop me. Stop me from going crazy. You can do it all. I'm doing it for room purposes. I don't have room to write the whole line up here, so I'm going to do 2 separate lines. Feel free to stay on one line on your paper. That's a solid. And then Mg plus 2 aqueous plus 2 nitrate aqueuses, aquei. All right. Can I cancel anything? Nitrates, I have 2 of them. I have 2 of them. And magnesium, I have 1 of them here and 1 of them here. So my final net ionic equation is 2 Ag pluses aqueous plus 2 Br minus aqueous gives us 2 AgBr solids. See, isn't this easier than last year? No? Yes? Yeah. Okay. Trevor. Oh, okay. Good question. Do you want to? I'm not going to count you wrong if you don't. Technically, and this is from grading the AP, there were times the kids had to come up with a balanced equation, and we took it if it's balanced. Nowhere did it say it had to be the lowest common factor for balancing, so I would take it. Yes. Okay. Potassium, metal, and water. I'm going to introduce you here to what I call a push-up problem. This is one thing I do in AP. For this particular type of reaction, because so many students miss it, and they miss it over and over again. So just like they do in your athletics, I decide, hey, I can make you guys do push-ups, right? Is that illegal? So if you miss this problem on the test or any test or quiz, a problem like this, and I'll explain what this problem is in a second, you get to do 5 push-ups. You miss it again, you do 10. You miss it again, you do 15, and so on and so forth. And I don't mean on the knee girly push-ups. These are real push-ups. Why do I do this? Because this problem, a metal plus water, is one of the most common reactions, and it's on the AP almost, it's on the AP a lot, and it's in different areas on the AP. And you need to know that when you put a metal in water, you make a metal hydroxide and a gas, okay? Here, let me show you what students do that's wrong. They'll do this. They'll be like, hey, K plus water. And they'll be like, okay, well, one thing you do need to do is, since this is a single replacement reaction, can potassium boot out hydrogen? Yeah, it's higher. It's more reactive. So yes, this reaction will happen. If it weren't, you'd write no reaction and move on with your life. But what they do is this. Ha! Boot it out. What do you think the product is they're going to write? K2O. No, it's not K2O. If you want to think of water as HOH, that might help you out a bit. So what's the product? KOH and hydrogen gas. Okay? Very important. So you've been warned. Push-up problems. All right, so potassium metal, what would the state of matter be? Solid. And water, water is liquid. All right, what are my products then, since this will happen and it is a single replacement reaction? Potassium hydroxide. Now, as far as acids and bases go, their solubility is based on their strength. They're all in solution, so they're always going to be aqueous. And I'll explain more of this on the next page when we get to acids and bases, but we'll go ahead and say aqueous. This is a strong base. And then what else do we have? Hydrogen gas. So we have to balance this. And it even helps in the balancing to think in your head HOH for the water, because you treat this as the OH and this is the H. So if I write this as HOH, I have 2 of the H's there, and then I need 2 of the OH's, and then I need 2 potassiums. It actually makes your balancing so much easier. Okay, there's not much to do on this one. There's only one thing we can actually dissociate into ions, which is what? The KOH. So with the KOH, we're going to split it and rewrite everything. And this is also going to be our final net ionic equation as well, because there's nothing that cancels. 2K plus aqueous plus 2OH minus aqueous plus H2 gas. So that's our final answer. I get satisfaction by crossing stuff out, so I'm not really happy right now. Okay, good. Can we move on? Yes. Next problem. Okay. Take a look at this problem. What are we mixing? What 2 classes of things are we mixing? Acid and base. What do acids and bases make? Water and a salt. Now, when I used to teach Chem 1, one of the most common things would be, regardless of what acid or base was mixed, because I said acids and bases make salt and water, they'd always write sodium chloride on the right side, no matter what the base or the acid. So that's amusing. So we're not going to do that. That would push me over the edge if you wrote sodium chloride and was mixing other stuff. So just keep in mind a salt is an ionic compound, so we're going to make a salt and we're going to make a water. Now, I'm actually going to change E, Kelly, and I'm going to make this sodium hydroxide and hydrochloric acid. We're mixing those. So I want to do this one first, okay? When I mix sodium hydroxide and hydrochloric acid, I'm mixing a strong acid and a strong base. I'm going to make note of this. That's not my real cough. That is a, you need to know this cough. All right? I want you to identify the strength of your acids and bases before you do the problem. So since we have sodium hydroxide is a strong base, 100% dissociates. Bam. Hydrochloric acid, is that strong? Yes. It's one of the strong binary acids, 100% dissociates, so it's aqueous. Bam. What are my products? Salt and water, and actually table salt this time. So we make sodium chloride, and we know, is that soluble or not? Have you ever swam in the ocean? Yes. Group 1, Big Daddy. And then, what's my other product? Water, and then that is liquid. Okay, so is this balanced? Yes, it is balanced. So I'm going to go ahead and split up my ions. Na plus aqueous plus OH minus aqueous plus H plus aqueous plus Cl minus aqueous makes Na plus aqueous plus Cl minus aqueous. And then what do I do to water? Leave it. Leave it be. What cancels? I heard chloride. I heard sodium. That's it. So I end up with my final answer, OH minus aqueous plus H plus aqueous gives us H2O. What's another name for an acid-base reaction? Neutralization. Do you see why? Does it make sense that here we're making water and this is a neutralization reaction? Someone last period said, could you drink that? Like, well, yeah, you could if you use the appropriate proportions and don't have something in excess, right? You don't want to mess up and have extra acid floating around. Yeah, you'd want to use the exact proportions. Now, here's another thing. This net ionic right here is the net ionic for every single strong acid and strong base reaction on the planet. You could take any strong acid and any strong base, write them out, and that's what you're going to get. Why? Because strong acids and bases dissociate. So those ions are going to all cancel except for whatever is needed to make up the water. So here's a gift to you, which this is like a double-edged sword gift. If you recognize your reaction is a strong acid or strong base, and you just go straight to writing that, I'm okay with that. You don't have to show all that work. But I'll show you where it's going to bite you. And it's going to bite you up here. Here, what are we mixing? Strong base with what? A weak acid. Here's the deal. Because this is a weak acid, you cannot just say, oh, H plus OH makes H2O. You can't. Okay? And my fear in telling you this is that you're going to apply that to something like D, and then you'll be wrong. All right? So be very careful at classifying your acids and bases. So let's start out with this. Sodium hydroxide we know is strong, and it dissociates 100% aqueous, makes an aqueous solution. Here's the thing. Phosphoric acid. What's the formula? H3PO4. What do we write next to it? Well, remember, aqueous just means it is soluble in water, right? If I go to the back, I can pull out a bottle of phosphoric acid, concentrated phosphoric acid. And it's a liquid, and it's in solution, right? So by definition, that's still aqueous. The thing about it is, within the liquid itself, the majority of those those phosphoric acid molecules are together. They're not dissociating into ions. So what that's going to do is that in our next step, we're not going to split it into ions. We're going to leave it together, but it's still considered aqueous because I still have a solution of it. Can y'all accept that and live with that? Because there's water with it. So it is dissolved in water, kind of like sugar. Sugar is not splitting up into ions, right? So if we were to write sugar up here, you'd write aqueous, but we wouldn't split it into ions because it doesn't dissociate into ions. Make sense? Okay. So what are our two products then? Sodium phosphate, Na3PO4, what? Good. And then, let me move this, and then we're going to make water liquid. Okay. Sodium hydroxide. Oh, this is not balanced. We need to balance this. So we need 3 NAs, and then 3 waters? Yes. Okay, so let's go ahead and split this into ions. 3 Na pluses aqueous plus 3 OH minuses aqueous plus. This is where you need to be careful. I know I said it was aqueous, but it doesn't dissociate into ions. H3PO4, aqueous. Now we're going to split up our sodium phosphate, and we get 3 Na pluses that are aqueous, and 1 phosphate that's aqueous, and 3 water liquids. What cancels? Sodium. And that is it. That's depressing. So our final net ionic equation, 3OH aqueous plus H3PO4 aqueous gives us 3H2O liquid plus PO4 minus 3 aqueous. So you see how that does not at all resemble this? So be careful with that whole strong, strong thing. It's got to be strong, strong in order to assume it looks like that. All right, I want to do one more problem just to kind of shorten our Monday a little bit, because we'll be talking about different types of titrations on Monday and doing some simple stoic on Monday. I want to, now that we've kind of reviewed double replacement reactions, I want to do number 9. And in order to do this problem, we have to write reactants and products and balance and the whole bit, and then we can do our stoichiometry. So it says, calculate the mass of silver sulfide produced. What does that mean? It's a product. Silver sulfide's formula is Ag2S. So we're looking for the mass of this produced when 18 grams of silver nitrate, 18 grams of silver nitrate is added to excess sodium sulfide. What sodium sulfide? Okay, 2S. I need a balanced equation, so what's the dealio? Is that the equation? Yeah, we have another product. We need sodium nitrate. So now we can balance this. So I need 2 silvers, which leads to me needing 2 nitrates, which takes care of my sodiums. So now I can just do the general, what we've already done last unit, general stoic. Starting out with my 18 grams, get out your calculators, 18.0 grams of AgNO3. We don't have to worry about limiting reagent. Why? Because sodium sulfide is in excess. All right, I want to cross the mole bridge, but I can't. So I need to convert to moles. For every 1 mole of AgNO3, I have point what? Okay, grams of AgNO3 cancels. And now I can cross my bridge. For every 1 mole of silver sulfide, I have 2 moles of AgNO3. Those cancel. And then I'm looking for grams. For every 1 mole of Ag2S, I have, thank you, 247.81 grams of Ag2S. Okay, let's multiply. And to 3 sig figs, how many grams of Ag2S did I produce? So 13.1. I wasn't sure if you said 9.3 or 1.3, so I didn't know, write down 1 or 2. All right. So starting on Monday, we're going to do more of these kinds of things, talk about what a titration is, and get into that. Have a good weekend.